We are now going to have a next lecture, the next Laudatio. And we'll get the microphone transferred. And this next Laudatio is on the work of Manjul Bhargava by Dick Grossi. You have the floor, Dick.
Thank you, Ingrid. It's a great pleasure to be able to present to you the work of Manjul Bhargava. He's, over the past 15 years, he's created a fantastic body of work that's made fundamental contributions to several areas in number theory. So among those, there are four that I'm going to discuss for you today. He generalized Gauss's famous composition law for binary quadratic forms. He counted number fields of small degree with bounded discriminant. He bounded the average rank of elliptic curves over the rational numbers, the rank of the group of rational points. And he has shown that most hyperelliptic curves of higher genus have no rational points at all. These are all extremely important contributions to the fundamental areas of the subject. But what's more important is that he's created a method. And this method combines very detailed studies of integral orbits and finding arithmetic interpretations for these integral orbits in group representations with techniques from the geometry of numbers. It's just a whole panoply of mathematics. In integral orbits, it involves algebra, arithmetic, representation theory, and the enumeration of those orbits involves new ideas in geometry and analysis. It's just beautiful work. Now, before I discuss these results of Manjul's, I want to review for you the first case where integral orbits were studied in mathematics and where the geometry of numbers was used to enumerate them. And that goes back over 200 years to the work of Lagrange and Legendre and Gauss on binary quadratic forms. Binary quadratic form is a quadratic function in two variables, x and y, with integer coefficients a, b, and c. And some definitions. Well, first, to a form, we have its discriminant, which tells you the quadratic extension where the form has its two roots. We say a form is positive definite if it only represents positive integers. No matter which integers x and y you put in, the quadratic form takes positive values. That occurs when a and c are positive and when the discriminant is negative. And in this talk, I'm only going to talk about positive definite forms. And also we say a form is primitive if the greatest common divisor of the coefficients is 1. That means that the integers that it represents are not all divisible by some number bigger than 1. So the fundamental work of Lagrange and Legendre studied the action of the group SL2. Actually, they studied the group of 2 by 2 integral matrices, which were invertible GL2, on binary quadratic forms by changing basis. This quadratic form just gives a quadratic function on a free module of rank 2 over the integers, and you can change basis and you represent the same integers. And they considered two forms equivalent. Let's say two forms are equivalent if one is taken to the other by an element in SL2. And that's the group action. And they proved, first of all, that every orbit contained a unique representative where the coefficients satisfied these inequalities. Those are called reduced forms. Another way of saying this is if you take the two roots of a reduced form, one of them lies in the fundamental domain that everyone writes for SL2Z on the upper half plane. And from this result, it follows very simply that there are only finitely many orbits with a fixed discriminant. Indeed, for a reduced form, 3 times AC is less than the absolute value of the discriminant. And that gives only a finite number of possibilities for the integers a and c, and then only a finite number of possibilities for b. So those results are due to Lagrange and Legendre, but the most important result was found by Gauss in the disquisitiones. Now, the group action preserves primitive forms, so you can restrict to the orbits which are primitive of a given discriminant. And he showed that that finite set of orbits had the structure of an abelian group under a law that he called the composition of binary forms. You could take two forms and compose them to get a third with the same discriminant. And this composition law, if you knew the orbits of the first two forms, you knew the orbits of the composed form. And that law gave a group structure on this finite set. Almost half the disquisitiones is devoted to binary quadratic forms. And the material on Gauss composition was considered the most difficult section of the disquisitiones, occupies several 20 or 30 pages. Now, nowadays we would say that this is a group action and we're classifying the integral orbits. It's an action on the symmetric square of the standard representation. That's binary quadratic forms. And we have an interpretation of Gauss's theorem of composition in that we know, following Dedekind, that the primitive orbits of the given discriminant turn out to correspond bijectively to the elements in the ideal class group of that quadratic ring of discriminant D. The ideal class group is the quotient group of the group of fractional invertible ideals by the subgroup of principal ideals. That's a much simpler definition. But if you actually want to work out the structure of that abelian group, you go back to Gauss composition because that's what works as an algorithm to calculate. Now, Gauss asked, after all this structure was determined, at the end of the disquisitiones, he asked, how large is the class number? It's a finite number. How many orbits are there of a given discriminant? And this was the kind of question Gauss loved because it was amenable to computation. And he computed for thousands and thousands of discriminants. And he convinced himself that the class number was growing at essentially the same rate as the square root of the absolute value of the discriminant. Now, he couldn't prove that, and we can't prove it effectively today. But he did prove a result that convinced him it was true on average. Namely, he stated the following result, that if you took the sum of the class numbers for absolute value discriminant less than t, it was a constant, pi over 18 times t to the 3/2 power. If you integrate a constant times x to the 1/2 power from 0 to t, you get a constant times x to the 3/2 power. And so we don't have Gauss's proof of this result. It's just a statement. But we suspect that he used the geometry of numbers to do it, because he had also worked on a famous problem he called the circle problem, which was to estimate the number of integral points inside of a circle of radius r. Since each square occupies something of area 1, your first guess would be the number of integral points inside the circle is pi r squared. Of course, that's not exact, but Gauss was able to prove that the error term was less than a constant times r, the radius. We actually suspect the error term is much less, but that's still an unsolved problem. But the simplest fundamental idea in geometry of numbers is to estimate the number of integral points in a bounded region. The first guess would be the volume of the region. Now, let's go back to his statement, and I'll give you Merton's proof. Well, first of all, the sum on the left-hand side, by the theorem of reduced forms, is just the number of points in this region in 3 space, where x, y, and z are bounded by these inequalities. That's the reduced form. And then the discriminant in absolute value is less than t. And that's a region that turns out to have finite volume. And if you're good at triple integrals, or you know how to use Mathematica, you can compute that its volume is pi over 18 times t to the 3/2 power. Now that would give an argument to show that the number of integral points was approximately that volume if this were a bounded region. But it isn't. It has cusps. Here's a projection of, here's what the region looks like for y equals 0, the area under that hyperbola. And so when you have a region with finite volume which has cusps, you have to be extra careful in using the geometry of numbers, because a priori there could be an infinite number of integral points far out in a cusp that had essentially volume 0. In this case, there aren't, and that's the final part of the argument. And all parts of this argument are going to be used by Bhargava in much more sophisticated examples than this simple representation. Well, enough of the history. Let me tell you a little bit about Manjul's work. In his thesis, he found a fantastic reformulation of Gauss composition, maybe the first progress on Gauss composition for 200 years. And he studied the action of 3 copies of the group SL2Z, acting on a representation, an integral representation of dimension 8, the tensor product of the 3 standard representations. Now, here's how he looked at it using his version of cubes. A vector in that representation, there's 8 integers, can be viewed as a labeling of a cube. And you can slice a cube 3 different ways: front, back, left, right, top, bottom. And each way you slice it gives you 2 2x2 matrices. Here they are. Here's the front, back, the right, left, top, bottom. And to a pair of 2x2 matrices, you can make a binary quadratic form by taking these determinants. m1x minus n1y. Take the determinant of that. That gives you a quadratic polynomial in x and y with integer coefficients. And so, from a vector in the cube, you get 3 binary quadratic forms with integer coefficients. Now, the first thing you show, which Manjul observed easily, was that these forms all have the same discriminant. All 3 of these forms have the same discriminant, and that gives a quartic polynomial in the coefficients of the cube, which is a polynomial invariant on the representation. But they're not arbitrary forms of that discriminant, because they're all made from the same 8 integers, so there must be some relation between them. He also observed that if you take the orbit of the vector under the action of the group on this representation, you get 3 different binary forms, but they're all in the same classes. So you really get from the orbit of the vector 3 different SL2Z equivalence classes of binary forms. And so 3 ideal classes for that quadratic ring. And the key relation that he noticed was that their product is 1. And in fact, that every triple of ideal classes with product 1 came from this representation. So the orbits on this representation are in bijection with triples of ideal classes, given by these 3 binary forms, with product 1. Another way of saying that is, if the product of the forms is the trivial class, and that's the class that represents the integer 1, then the 3 forms come from a cube. And this is a fantastic symmetric reformulation of Gauss composition, which simplifies all the formulas in the disquisitiones and is much more amenable to computation. Well, that was just his PhD thesis. Manjul didn't stop there. He found 14 integral representations that had a lot of similarities to Gauss composition. They don't compose anything anymore, but he could parameterize the orbits in terms of arithmetic data. For example, if you take this representation and you restrict to the diagonal SL2, this tensor product of 3 representations is no longer irreducible, but it has an irreducible piece, which is the symmetric cube. And that gives the action of SL2 on binary cubic forms of this type. What are the orbits? Well, the 3 ideals are the same. So you just get a quadratic ring and an ideal class whose cube is 1. And so this representation parameterizes quadratic rings and ideal classes of order 3 in that ring. Well, among these 14 representations, there were 3 very special ones. And they're the action of GL2 on ternary quadratic forms, the action of SL3 cross GL2 on pairs of ternary ternary quadratic forms, and the action of SL5 cross GL4 on 4 tuples of exterior 2 forms on 5 space. Now, where did they come from? Well, it turns out that all of these 14 representations, Bhargava discovered, occur inside of Chevalley groups. They occur with the action of the Levy factor on the unipotent radical of a parabolic. And these 3 occur in the exceptional groups G2, F4, and E8. And they occur in the only parabolics that are both maximal and special in the entire theory of Lie groups. And they have wonderful, wonderful properties. For example, they each have a polynomial invariant that generates all the others of degree 4, 12, and 40. Notice that that's the same degree as the dimension of the representation. And they have finite stabilizers of the orbits where the discriminant is non-zero. And Manjul proves that the orbits of these three representations correspond bijectively to cubic rings, quartic rings, and quintic rings, rings which are free Z modules of rank 3, 4, and 5. And this invariant is just the discriminant of the ring. Now recall that if you have a ring which is a free Z module of rank n, you can define its discriminant by the determinant of that symmetric n by n matrix of traces. Well, this theorem was known for n equal 3. It had been proved by Delone and Fadeev. But the quartic and quintic cases were infinitely more complicated because you didn't just get a ring, you got a ring with additional data. In the quartic case, a cubic resolvent. In the quintic case, a sextic resolvent. And the algebra involved in passing from these orbits to the ring is just phenomenal work. But then, Bhargava decided to use the argument of Gauss and count these rings using the geometry of numbers. And he used this to enumerate number fields which have small degree. So to recall, for those of you who haven't studied number theory, a number field is just a field which, as an extension of the rational numbers, is a finite dimensional vector space. And that dimension is called the degree of the field. And inside of every number field, there's a natural ring of rank n, which is called the ring of integers. It consists of all the elements that satisfy integral equations over the integers. And since we can define the discriminant of a ring of rank m, we can define now the discriminant of a number field by taking the discriminant of its ring of integers. And those are the two fundamental invariants of a number field, the degree and the discriminant. They're the first thing you define in a course on number theory. But we know very little about them. For example, we suspect that if you take all the number fields of a fixed degree and you bound their discriminant by t, that the number of such fields grows like a constant, depending on n, times t. That's known for quadratic fields, where it's easy, and it's known for cubic fields. That was proved by Davenport and Heilbronn. But Bhargava proves it for all fields of degree less than or equal to 5, and his work leads to a guess of what the constant is in general. The constant is always given by a product of local terms. So for example, for degree 5, the constant is this. Now, how does he prove this wonderful result? Well, he does the same as Gauss did. He takes the representations he used to parameterize cubic and quartic and quintic rings, and in each case, he constructs a fundamental domain in the real representation. That's like the reduced forms. And then he calculates the volume of that region if you bound the height by t. That was like Gauss's computation of the volume of that region. And of course, the region has cusps, much more complicated than the case of binary quadratic forms. So he has to estimate the number of integral points in a cusp to show that it doesn't screw up the volume estimate. And finally, that's just counting the rings of rank n. He has to introduce a sieve to count the rings which are maximal and are integral domains. It's a fantastic generalization of Gauss's work. But all of those representations, all of the representations he found that generalized Gauss composition, I should say Gauss composition comes from the exceptional group of type D4, where the parabolic subgroup has triality operators, and that's what gives the 3 different ideal classes. All of these representations have the property that their invariant theory is very simple. There's a single polynomial that generates all the ring of invariants. But then he took a look at the most famous representation that has 2 polynomial invariants, and that's related to elliptic curves. Now, Manjul is going to talk about this in his talk at the Congress, so I can be brief. In any case, he'll do it much better than I would. So I urge you very strongly to go to his talk on Friday at 11:30. If you haven't been to one of his talks, you're in for a real treat. Now, the simplest representation, which has 2 independent invariants, is the action of SL2 on binary quartic forms, or what we would say is the symmetric 4th power. There are 2 invariants which are independent. One is of degree 2, one is of degree 3. And the polynomials in A and B generate all the invariants. And there's a famous polynomial of degree 6 called the discriminant, which is the discriminant of the quartic form, whose non-vanishing determines the orbits that we would now say are stable in the sense of geometric invariant theory, subject discovered or developed by David Mumford. And that means that the orbits are closed and they have finite stabilizers. In this case, the stabilizer is order 1, 2, or 4. Now, associated to each stable orbit, you get an elliptic curve defined by this equation, because the discriminant being non-zero says that that cubic equation has 3 distinct roots. And when you have an elliptic curve over the rationals, you may want to know what are the rational solutions of that equation. And what's wonderful about elliptic curves is that the space of rational solutions forms an abelian group. There's a group law because if you take any line through 2 points on the curve, it meets the curve in a 3rd point, which isn't, and the sum of those 3 points is 0 in the group law. So the sum point is what you obtain by projecting across the x-axis. And this abelian group has a beautiful structure. Mordell proved about 100 years ago that it was finitely generated. So it has a certain number of independent generators and a finite torsion group. The torsion group is known. That was work of my colleague Barry Mazur. It proved that it had order less than or equal to 16. But we know very little about the number of independent generators, which we call the rank. When the rank is 0, that means it's a finite number of solutions. When the rank is positive, an infinite number. So is the rank bounded, for example, if we look at all elliptic curves over the rational numbers? The answer is that no one knows. There are people who believe it's bounded. There are people who believe it's unbounded. The current record is held by my colleague Noam Elkies, who found an amazing curve of rank 28. And another question we might ask is, what's the rank on average? If we looked over all elliptic curves and averaged by letting the coefficients a and b get larger and larger as integers. And people had guessed that perhaps the rank on average was a half. That in the sense of proportion, 50% of curves should have rank 0 and 50% should have rank 1. That doesn't mean that none of the curves have rank 2 or more, just that they're very sparse. Well, as Manjul will show you in his talk, the computational data didn't really support that, but his results do. And he proved a wonderful, wonderful theorem with his student Arul Shankar, who's also at this Congress, by studying the orbits on this representation of binary quartics and also ternary cubics. And they proved that the average rank is less than 1. Now, before this result, no one could even prove that the average rank was finite. Perhaps as you let a and b get large, the rank kept getting larger and larger. But this is the first piece of evidence that perhaps the average rank is a half. And they prove stronger than this, namely a positive proportion have rank 0, so have only finitely many points, and a positive proportion have rank 1, so have an infinite number of points. And they also prove that at least 80% have rank either 0 or 1. I should say that recently, and this I believe will also be covered in Bhargava's talk, they've compared these results to results that have been known on the conjecture of Birch and Swinnerton-Dyer, which predicts the rank in terms of the number of points taken modulo primes. And they now have Manjul has a result with Chris Skinner and Wei Zhang that the conjecture of Birch and Swinnerton-Dyer is true for 66% of elliptic curves over the rationals. This is just unimaginable work. No one even thought in these directions. And I'll finally finish with his work on rational points on hyperelliptic curves. So this just to show you that the theory isn't limited to genus 1. A hyperelliptic curve is given by an equation y squared is a polynomial in x, where the polynomial has non-zero discriminant. And the degree of that polynomial I've made even, that defines what's called the genus of the curve. And Faltings had proved in '83 that if the genus was at least 2, the number of rational solutions of this equation was finite. There are only finitely many values of x where when you put them in that polynomial, you got a square. That's the Mordell conjecture for curves of genus at least 2, and that was awarded a Fields Medal at the Congress in 1986. Well, Bhargava showed much more. He showed that a majority of these equations have no solutions whatsoever. Namely, for no value of x when you put it in this polynomial, is it going to be a square. And not only is it a majority, meaning more than 50%, but it tends to 100% very quickly. Namely, once you get the genus to at least 10, at least 99% of hyperelliptic curves have no rational points at all, which teaches us that if we're going to work with the arithmetic of curves, we better learn how to work with curves that have no rational points. So it's been a real pleasure to try to give you some idea of Manjul's work. I want to end with a quote from another number theorist who wrote me the sense about his work, the sense of a new field opening up before one's eyes with an elegance and clarity that remind one of one's first encounters with classical mathematics is unique and sometimes breathtaking. That comes from Andrew Wiles, who was Manjul's thesis advisor at Princeton. I think all of us feel the same way. As I say, it's an honor to speak on his work and a pleasure to speak in front of you. Thank you.
Thank you so much, Dick.
Dear colleagues, it is a privilege to introduce Professor Manjul Bhargava. Professor Bhargava received his PhD from Princeton University in 2001 and was appointed professor at Princeton in 2003. He obtained spectacular results in arithmetic geometry, geometry of numbers, a discipline with roots in ancient Greece, developed by mathematical giants Minkowski, Mordell, Siegel, Weyl, Faltings, Wiles, and many others. His work has been recognized with many prizes and distinctions, including the Ramanujan Prize, the Cole Prize in Number Theory, the Fermat Prize, and the election to the US National Academy of Sciences in 2013. And now, at this Congress, he has been honored with the highest prize in mathematics, the Fields Medal. Professor Grossi gave a wonderful description of Professor Bhargava's work on the opening day of the Congress. To this description, I would like to add the following lines by Plutarch. It is not possible to find in all geometry more difficult and intricate questions, or more simple and lucid explanations. Some ascribe this to his natural genius, while others think that incredible effort and toil produced these, to all appearance, easy and unlabored results. No amount of investigation of yours would succeed in attaining the proof, and yet, once seen, you immediately believe you would have discovered it. By so smooth and so rapid a path, he leads you to the conclusion required. Dear colleagues, please welcome Professor Manjul Bhargava.
Can everyone hear me okay? In the back? Okay. Okay, well, thank you very much for that introduction. It's a great honor to be speaking on this occasion. I want to begin by thanking the organizers of this ICM, especially Ingrid Dobeschies and Hyungju Park, for everything they've done to make this ICM so wonderful. Yeah, Toby. And even for each of the speakers individually, they made sure that everything went totally smoothly for us. So in addition to organizing the entire ICM, they have been just incredible hosts. I also want to begin by thanking my teachers and my mentors and colleagues and friends and students and postdocs, many of whom are here in the audience today, for all their support and collaboration. And of course, I want to thank everyone in the audience, again, for all the support and for being here. So what I want to talk about today is a very classical question in mathematics, in particular in the area of number theory. The question is, given a mathematical expression, does it take a square value? So this theme of understanding square values of polynomial expressions in the whole numbers, this goes back thousands of years and has had many applications, not just within number theory, but even outside number theory. So the question is, looking for square numbers taken by a polynomial. So this is a continually recurring theme since ancient times. And one of the very first examples that seems to have arisen of looking for square numbers of a polynomial expression seems to occur in what are called the megalithic monuments of Egypt and Northern Europe. So in these huge stone structures that were built at that time, there are many right triangle shape structures, and the length of these stones, so there are these huge right triangles made of stone, and the lengths of these stones all seem to be integer multiples of a certain basic unit that was used at that time. And so what that means is that it seems the monument builders were finding solutions, integer solutions, to c squared equals a squared plus b squared in whole numbers a, b, and c. And they constructed these solutions explicitly in stone. So of course this is all speculation in the sense that there's no written record that they actually wrote down these solutions, but if you look at the stones and measure their lengths, it's pretty convincing that they had some idea of how to construct integer length right triangles and therefore look for solutions to this equation c squared equals a squared plus b squared. In other words, looking for square values of this two variable polynomial a squared plus b squared. And this is back in 2500 BC. Of course, as I said, none of this was written down. It was constructed in stone. The first written record of finding solutions to c squared equals a squared plus b squared occurs at least as far back as 1800 BC. So in about 1800 BC, there was a Mesopotamian tablet known as Plimpton 322. This is a tablet that's kept in New York City at Columbia. And it dates to 1800 BC, and it listed numerous such triples, A, B, C, that satisfy c squared equals a squared plus b squared. And here are some examples of solutions that were on this tablet. As you can see, some of these solutions were pretty big. Many were up to 5 digits for A, B, and C. And it's hard to come up with such solutions randomly. They seem to have some systematic method of finding such solutions. That central one there is pretty impressive, I think. Here's what the tablet looks like. This is the one that's kept in Columbia. So you can see they didn't quite write the numbers the way we do now. But if you translate the triples that are written there, they're exactly the triples that I showed over here. So that's one classical example, and that came up in many cultures throughout history, finding solutions, whole number solutions to c squared equals a squared plus b squared. So that's a very influential example. It comes from what's called the Pythagorean theorem, that predates Pythagoras, which is, so when is a squared plus b squared a square? Another classical example of a square equation, an equation where we're interested in finding square values, is what's known as Pell's equation, which of course also predates Pell. And so in that, the question is, how can we find all square values taken by the polynomial n y squared plus or minus 1? So when is n times a square very close to a square? That's the question. And so there's a theorem, it goes back to Brahmagupta, about 600, in the year 600, which is that if you have a non-square integer n, then there are always infinitely many solutions. In other words, there are always infinitely many values of y, such that ny squared plus or minus 1 is a square. And Brahmagupta gave an explicit way to find them all. So that's another example of an equation that's been very influential in number theory ever since, and even outside number theory. For example, in the solution to Hilbert's 10th problem by Manjul, the structure of solutions to x squared equals ny squared plus or minus 1 played a very important role. So it's had influences even outside number theory. And finally, I'll give one more example. Fermat's equation. So Fermat showed that the expression a to the 4 plus b to the 4 never takes a square value. So in particular, he proved Fermat's last theorem for the exponent 4, right? Because if a to the 4 plus b to the 4 never takes a square value, it never takes a 4th power value. And therefore, c to the 4 equals a to the 4 plus b to the 4 never has a solution. So, of course, you know that equation as well has had a very important influence in mathematics and modern number theory. And also the method that was used to solve this equation, namely Fermat's method of descent still plays a very important role today in many aspects of number theory. Okay, so these are three classical examples of square equations. In other words, polynomials where we're interested in understanding what are the square values taken by that polynomial. And as I said, they've played a very important role throughout the history of mathematics, and the methods that were used to solve them still play an important role today, both in number theory and outside number theory. Let me give you one more example of a square equation, a mathematical expression where one has been interested in knowing the square values. It's called the Ramanujan-Nagel equation. So in 1913, Ramanujan posed the following problem in the Journal of Indian Math Society. So the problem asked to show that the values of n such that 2 to the n minus 7 is a square. So what are the values of n such that 2 to the n minus 7 is a square? And the problem was to show that the only values of n for which this integer is a square are n equals 3, 4, 5, 7, and 15. So you can check that these values of n do in fact give squares. Right? 2 cubed minus 7 is 1 squared, 2 to the 4 minus 7 is 3 squared, 2 to the 5 minus 7 is 5 squared, and 2 to the 7 minus 7 is 11 squared, and 2 to the 15 minus 7, well, it's 32,761, which is of course 181 squared. And Ramanujan claimed that there are no other solutions. This problem remained unsolved that year in the journal. But 35 years later, the problem was solved and was proved in the positive by Nagel in 1948, using some very novel methods in Diophantine analysis, which have since influenced the field quite heavily. And yeah, so this problem continues to generate much research due to the methods that were introduced to solve it. So this is a very different kind of equation. It's called an exponential Diophantine equation because one of the main variables, n, is in the exponent. And that can complicate things when your variables are in the exponents. So equations of this form, y squared equals a to the n minus b, for fixed a and b. So if you have constants a and b and you're trying to solve y squared equals a to the n minus b for integers y and n, these are called equations of Ramanujan-Nagel type. And when a equals 2, which is so in other words, looking at equations of the form y squared equals 2 to the n minus b, it's now known that there can be at most 2 solutions to that equation, unless b equals 7, in which case there were 5 solutions, as Ramanujan found. So the example that Ramanujan put forth was not a random one. It was very special. It's the only such equation that has so many solutions. Typically, it's now known that you can have at most 2 solutions. But the kind of question I want to ask today is to say, well, what happens typically? This result just says that there are at most 2 solutions, but typically, probably there are no solutions. And that's the kind of question I want to ask today. Are there usually 0 solutions to the equations of Ramanujan-Nagel type? And probably the answer is yes, and that's the kind of question that I want to ask in this lecture. What happens with typical equations rather than particular equations? And I'm going to stay away from exponential Diophantine equations. I just wanted to give you a flavor of these examples of square equations that come up in mathematics. But today, I want to talk, instead of exponential Diophantine equations, I want to talk about the simplest kind of square equation, namely where we wish to determine whether a polynomial in one variable, just one variable, takes a square value. So you're given a polynomial in one variable. How often does it take a square value? Does it take a square value at all? So an equation in x and y of the form y squared equals a polynomial in x is called a hyperelliptic curve. The reason is that if you graph the equation y squared equals f of x, where f of x is a polynomial, you get a curve in the real plane. And the hyperelliptic refers to the fact that this curve has a symmetry. If you have a solution x comma y, and you replace y by minus y, you still have a solution. So the graph of this equation is symmetric about the x-axis, and that's what the hyperelliptic refers to. Okay, so y squared equals f of x, the graph of that is called the hyperelliptic curve. And when we're looking at such equations, y squared equals f of x, I just want to say that it suffices in these kinds of questions to assume that f of x is square free, that it doesn't have multiple roots. Because if f of x had a square factor, you could absorb it into the y squared, okay, and then solve that equation. Okay. So you can always assume, and I'm always going to assume in this lecture, that f of x is a square free polynomial. It doesn't have multiple roots. Okay, so if we're trying to solve y squared equals f of x, find solutions to that, those solutions are called points on the curve. Because when you graph it, those, the ordered pair x comma y will be a point on that curve that you've graphed. Okay, so those solutions are called points on the curve. And we're interested in finding all integral solutions to y squared equals f of x. That is, all integral values, whole number values of x, such that f of x is a square. Or more generally, we can look for all rational solutions to y squared equals f of x. Okay, so f of x will be a polynomial, say, with rational coefficients or integer coefficients, and we're interested in the rational number values of x such that f of x is a rational square. Okay, so when does f of x take rational square values? So such rational solutions, they correspond to rational points on the hyperelliptic curve. In other words, they correspond to points on the curve, both of whose coordinates are rational. Okay, so finding rational solutions to y squared equals f of x, that's the same thing as saying finding rational points on the curve. Okay, so that's the subject of this lecture. We want to understand when an integer polynomial takes square integer values or a rational polynomial takes rational square values. Okay, so the first question to ask is how many rational points can a hyperelliptic curve have? How many rational solutions can y squared equals f of x have? Well, more generally, we can ask how many rational points can a general algebraic curve have? If we graph h of xy equals 0 for some polynomial h in two variables, then that gives a curve in the plane again, and we can ask what are the rational points on that curve? In other words, what are the rational solutions to h of xy equals 0? So this question about the possible number of values, possible number of solutions to h of xy equals 0, in other words, the possible number of rational points on an algebraic curve, turns out to have a beautiful answer in terms of the graph of the solutions of h of xy equals 0. But we have to do this graphing not in R2, but in C2 in order to state this answer. And so that's what I want to tell you first. So to state this answer about the possible number of rational points on a general algebraic curve, h of xy equals 0, we need a notion from topology, namely that of the genus of an algebraic curve. So recall that when we graph h of xy equals 0 in R2, we get a curve-like figure in the plane, we get a curve, and that's why such an object is called an algebraic curve. But algebraic curves are also called something else. They're called Riemann surfaces. And let me explain. So instead of saying curve, so sometimes mathematicians regret this terminology that we call them curves because the correct place to graph h of xy equals 0 is really in C2 rather than R2, so that you get really the full set of solutions over an algebraically closed field. The situation is analogous to when we look at polynomials in one variable. There's the fundamental theorem of algebra that says the number of roots is the degree. But of course that statement only holds when you work over the complex numbers, not over the real numbers. And same thing for two variable polynomials. To really see all the solutions, to see the full structure, you need to graph, you need to look at your solutions over C2. But of course if you graph h of xy equals 0 in C2, the graph that you would get would not be a curve, but it would be a two-dimensional real surface. And that's why the graph in C2 is also often called a Riemann surface. Now C2 is a four-dimensional real vector space, and so for most of us, at least for me, it's hard to visualize. For those of us who live in a three-dimensional world, it's hard to find graph paper that's four-dimensional. But the graph of h of xy equals 0 is actually not so hard to visualize, because even though it's sitting in this 4-dimensional real space, in the end it's a 2-dimensional real surface. So it's a 2-dimensional object, and so in that sense, it's actually not very hard to visualize. Okay? So when you have an equation of the form h of xy equals 0, the natural thing to do is to think of it as a surface sitting in C2. Okay, the graph of the solutions are a surface in C2. And what does that surface look like? So this is the fundamental theorem about what the surface looks like. The graph of an algebraic curve in C2 is topologically a surface with G holes, G donut holes, perhaps with finitely many points removed. Okay, there may be some finitely many punctures, but it's a compact surface with G donut holes, G handles. And so that number G occurring in the theorem is a fundamental topological invariant of this graph, which is called the genus of the curve. And here are what the graphs in C2 of algebraic curves of genus 0, 1, and greater than or equal to 3 would look like. So the first graph there is just a sphere, something topologically equivalent to a sphere. It has no donut holes, and so it has genus 0. The next one is the surface of a donut. It has one donut hole, so it has genus 1. And then the next figure has multiple donut holes, and so it has genus, well, it seems to have at least 3 holes there, and so it has genus at least 3. Okay, so that's what, so these are typical examples of what the graphs of h of xy equals 0 would look like in C2. And now here's the amazing thing. The genus, this topological invariant of the graph of h of xy equals 0 is related to the structure of rational points on the graph of h of xy equals 0. It's related to the rational solutions. So the significance of the genus is the following theorem that relates the genus of a curve to the structure of its rational points, of the rational solutions. So the theorem is that the set of rational points on an algebraic curve having genus G is either empty or infinite. Okay, only those two possibilities can occur if G equals 0. So if you have your h of xy equals 0 equation, you graph it in C2, it has no donut holes, then you know that it either has 0 rational solutions or it has infinitely many rational solutions. Okay, what happens in the case of genus 1? The answer is that you have either finitely many or infinitely many rational solutions. That's not saying very much. But here's the really amazing part of this theorem. The first two theorems are actually fairly easy. Second one, particularly easy. The third part of the theorem is that the set of solutions is always, set of rational solutions is always finite once there is more than one donut hole. Once the genus is more than one, there are always at most finitely many rational solutions. And this is a very deep theorem. It was conjectured by Mordell early in the 20th century, and it was proven by Faltings in 1983. So this is called Faltings' theorem. The number of rational solutions to a two-variable polynomial equation is always finite, provided that the graph in C2 has more than one donut hole, if the genus is bigger than 1. So this theorem is truly remarkable in that it relates the genus, which is a topological invariant of the locus of solutions in C2, to the structure of rational points, which is a number theoretic structure. And that's something that's really very beautiful about this subject, which is called arithmetic geometry, in that it relates number theoretic invariants, like rational solutions to equations, to topological and geometric invariants, such as the genus. I should mention that this theorem is effective in the case of G equals 0. If you graph your equation and you find that there are no donut holes, there is an effective procedure to decide whether there is a rational solution, in which case there'll be infinitely many, or whether there's not a rational solution. So in the genus 0 case, the theorem is effective. You can actually determine which case you're in, empty or infinite. But there's no known algorithm to determine how many rational points a curve has once the genus is at least 1. So in particular, when the genus is bigger than 1, you know there are finitely many solutions, but there's no known algorithm to find them with proof. And in particular, in the case g equals 1, it's not even known how to determine whether your equation has finitely many solutions or infinitely many solutions. So there's no known algorithm that'll take a genus 1 curve and tell you whether there are finitely many solutions or infinitely many solutions. We just don't know how to do that. Although the Birch and Swinnerton-Dyer conjecture, it turns out that gives a conjectural answer. It gives a conjectural algorithm that would work. But at the moment, it's not known how to even determine whether a genus 1 equation has finitely many or infinitely many solutions. Okay, so this is the fundamental theorem that guides you into at least saying what the possibilities are for the number of rational solutions. And it's broken up into the cases g equals 0, g equals 1, and then g bigger than 1. Okay. So let's specialize to the case of hyperelliptic curves. It turns out it's not very hard to visualize the graph in C2 of a hyperelliptic curve and see how many donut holes it has, and thus compute the genus of any hyperelliptic curve. And so I'll just tell you the answer. If you take y squared equals f of x, a hyperelliptic curve, where f has degree n, we assume square free, of course, as usual, then this curve y squared equals f of x, right? So this is the case where h of xy is y squared minus f of x, right? The genus of this curve, y squared equals f of x, is basically given by the degree. It's given by the degree minus 1 over 2, the integer part of that. So the genus basically grows like the degree over 2. And so it's a nice exercise to just visualize that and see that that's what's happening, that that's how many donut holes you get when you graph this in C2. And so if f has degree 1 or 2, the hyperelliptic curve has genus 0. If f has degree 3 or 4, the genus is 1. And if the degree is 5 or 6, then the genus is 2, and so on. Okay, so that's how you see the genus from, if you're given your polynomial, look at the degree, and you get the genus as roughly half of the degree. And so the corollary is that suppose f of x has degree n, then the set of rational points on the hyperelliptic curve, y squared equals f of x, is either empty or infinite, if n equals 1 or 2, right? That's the genus 0 case. It's either finite or infinite, if n is 3 or 4. And the number of solutions to y squared equals f of x is always finite, if n is at least 5, right? Because then the genus is at least 2. Okay, so that's the corollary for hyperelliptic curves. And as I already mentioned, in the genus 0 case, everything is effective. And so this case where of degree n equals 1 or 2, that means we completely understand that case. And it follows from what's called the Hasse-Minkowski theorem, that you can find all the solutions in that case. And in once the degree of f of x is at least 3, then as I said, there's no known algorithm to determine what the solutions are. And in the genus 1 case, the middle case, in other words, the degree 3 or 4 case, it's not even known how to tell whether there are finitely many or infinitely many rational solutions. Okay. But at least by degree, we now know at least what the possibilities are for the number of rational solutions. So as I said, the case n equals 1 or 2 is known and effective. You can determine all the solutions. So the first case of interest in some sense is the case of n equals 3. That there already we don't know how to tell whether there are infinitely many or finitely many rational solutions. And that special case n equals 3, the smallest case where we just have no idea what's going on, is called, such curves, hyperelliptic curves, are actually called just elliptic curves. So an elliptic curve over Q is a genus 1 curve that has an equation of the form y squared equals a cubic polynomial in x, okay, where these coefficients are rational numbers. That's what the over Q part is saying, that the coefficients are rational numbers. We can simplify the expression of this elliptic curve E by observing that we can scale x and y, and we can also translate x by a constant. By translating x by a constant, we can get rid of the x squared term. And then if we scale x and y, we can actually get rid of then the leading term, a0. And so we can assume in this equation that a0 is 1, and A1 is 0. And so the typical way that mathematicians often write elliptic curves over Q is just as y squared equals x cubed plus ax plus b. We've made the leading coefficient 1, and we got rid of the x squared term. So any elliptic curve over Q can in fact be expressed in the form y squared equals x cubed plus ax plus b, where a and b, you can actually assume they're integers by scaling x and y. So every elliptic curve over Q can be written as y squared equals x cubed plus ax plus b, where a and b are integers. And so we'll always write our elliptic curves that way. And this case of elliptic curves, the case n equals 3, right, degree 3, is very special for a number of reasons. First, it's the first case, as I said, where we don't know in general how to find all the rational solutions. Perhaps an even more important reason, it's the only case where the set of rational points on the curve, the set of rational solutions to this equation, has an additional structure, namely a group structure. So the set of rational solutions on an elliptic curve turn out to form a group in a natural way. And so I want to concentrate on this case for a few minutes. So first, just to give you a sense of what these things look like, if we graph an elliptic curve in R2, it tends to look like one of these two pictures. So either it has two components or one component. And how do you tell which one? So if you have y squared equals a cubic polynomial, you'll get the first picture if the cubic polynomial has 3 real roots. You'll get the second picture when the cubic polynomial has 1 real root. As you can see, if you look at the intersection of these curves with the x-axis, the first one has 3 intersections corresponding to the 3 zeros of your cubic polynomial, while your second one has just 1 intersection with the x-axis corresponding to just the 1 real root of the cubic polynomial. Okay, so that's what an elliptic curve tends to look like if you graph it in R2. Okay, so what is this group law on the rational points on an elliptic curve? So if one has 2 rational points on a plane elliptic curve, in other words, 2 rational solutions to y squared equals x cubed plus ax plus b, then the line connecting those 2 rational points, when you graph your elliptic curve and you graph your 2 rational points, the line connecting those 2 rational points will always intersect your elliptic curve in a third rational point. The reason is that it's a cubic curve. So when you solve for the point of intersection, you're going to be solving a cubic that already has 2 rational roots, and therefore will have a third rational root. So the line connecting 2 rational points on a plane elliptic curve always intersects the elliptic curve in a third rational point. And that's a way of taking 2 rational points and producing a third. So here's how you define the group law. Given rational points p and q on E, we can define a rational point p plus q on E as follows. We take p and q, we take the line connecting them. As I said, that line will intersect the elliptic curve in a third rational point. And what we do, we take that third rational point and we reflect it across the x-axis. And we call that p plus q. That will still be a rational point. Okay, and that's the law of addition. And one checks that together with this law, so one checks that this law of addition, together with the point at infinity as the identity. So what's the point at infinity? The point at infinity is the point that you get when you go all the way up the curve to infinity, or equivalently when you go all the way down. Okay, that's called the point at infinity. And if you take that to be the identity of this group law, then this addition law endows the set of rational points on the elliptic curve with the structure of an abelian group. So the fact that it's abelian is pretty clear by the definition of addition. P plus q is clearly the same as q plus p because the line connecting p and q is the same as the line connecting q and p. What's less obvious is that this law of addition that we just defined here is associative, that p plus q plus r would be equal to p plus q plus r. But that can be checked explicitly using coordinates. In the modern way of saying things, this group that we're obtaining is the divisor class group of the elliptic curve. Okay, so that's the group law on the rational solutions to an elliptic curve, the rational points on an elliptic curve. And so we can ask then, if we're given an elliptic curve, what does that group look like? What does the group of rational solutions look like? What is the structure? So for an elliptic curve E, the group of rational points on E is denoted by E of q. the rational points on E. So the group is called E of Q. And the fundamental theorem about this group, E of Q, the group of rational points, is what's called Mordel's theorem. It's proven by Mordell in 1922. And the theorem is that the group, E of Q, this group of rational solutions to y squared equals x cubed plus ax plus b, it's a finitely generated abelian group. So this group is always finitely generated. Okay, that's the remarkable thing here. And what that means, well, when you have a finitely generated abelian group by the fundamental theorem of finitely generated abelian groups, that means that E of Q as a group is isomorphic to z to the r, right? A finite product of cyclic groups, infinite cyclic groups, times some finite torsion group, finite abelian group. So since E of Q is finitely generated, E of Q is isomorphic to z to the r, some finite number of copies of z, times some finite group, T. And so these are natural invariants of the elliptic curve. We have R there, and we have T. Now, T was studied in some very deep work of Mazur. What Mazur showed is that the group T is always bounded in size by 16. And in fact, what happens, it's easy to show that T is in fact usually just trivial. It rarely is non-trivial. So what that means is that E of Q is generally just isomorphic to z to the r. And so this r is giving you a fundamental invariant of the elliptic curve. And r measures basically how big this group E of Q is, right? If r equals 0, what does that mean? That means that the group of rational points is finite. In other words, the elliptic curve has only finitely many solutions. Whereas if r is at least 1, then there are infinitely many rational solutions. And r measures how infinite that set of rational solutions is, right? The bigger r is, the more infinite it is. So this fundamental quantity r is called the rank of E. It measures how big the group of rational points is. In very elementary terms, the rank of E measures the number of points you need to start with on your elliptic curve, so that by just playing connect the dots, right? Taking pairs of points that you started with, connecting, finding the third point of intersection, and by keep doing that, how many points do you need to start with such that if you play this connect the dots games to keep producing more and more rational points, you get all of them. That's basically what r is measuring. And by Mordel's theorem, this number is always finite. In other words, on an elliptic curve, you can always start with just some finite set of rational points, such that all rational points can then be constructed from those finite set of rational points by continually drawing lines through pairs of those rational solutions to find the third point of intersection and repeating this procedure. So that's the rank, that's the number r. It measures the number of points needed to generate all rational points on the curve. And so we'd like to know, how does r typically behave? As I said, there is no known algorithm for a particular elliptic curve to determine r. There's no known algorithm if you're given the algorithm an elliptic curve to spit out r, to output r. But we can ask, what do we expect about r? So that's the question I want to ask today. Since we don't have an algorithm to determine r for a particular elliptic curve, I want to talk about what happens typically. What do we expect if we pick a random elliptic curve? How big do we expect r to be? So to ask this question more precisely, we want to know how we're going to sample elliptic curves at random. So recall that an elliptic curve E is defined by a cubic equation, y squared equals x cubed plus ax plus b, where a and b are integers. And remember, we always assume that x cubed plus ax plus b is square free. It has no multiple roots. And so its discriminant is non-zero. And the discriminant of x cubed plus ax plus b is minus 4a cubed minus 27b squared. So that we can assume is non-zero. Okay, so any elliptic curve can be written in that form over Q. And so we can define the height of E by the size of the coefficients of the defining equation. So more precisely, we define the height, h of E, to be the maximum of 4a cubed and 27b squared. So in other words, the maximum of the absolute values of the two terms in the discriminant. So the reason we don't define it just as maximum of the absolute values of a and b is that it's natural to compare a cubed and b squared. And so we define it more as maximum of the absolute values of a cubed and b squared. These constants 4 and 27 are not particularly important. They don't really change anything that I'm going to say. But they lead to more prettier formulas because they're the two terms in the discriminant. I should mention that there are various other notions of height of an elliptic curve. What I just defined here is called the naive height. There's also the Falting's height. There's the discriminant that I defined. Up on top, there's something called the conductor. So these are all alternate ways of ordering all elliptic curves by some notion of height. But any of these notions of height could be used instead for the questions that follow, but conjecturally they're not expected to change any of the answers. Standard conjectures would imply that no matter which of these notions of height you use, they're not going to change any of the answers to the questions that I'm about to ask. Okay, so we're going to write all elliptic curves in the form y squared equals x cubed plus ax plus b, where a and b are integers. And then we're going to let a and b grow. And we want to know how is that fundamental invariant R, the rank, varying? That's the question. In particular, we can ask, what is this average value of this invariant R? What is the average rank? Okay. So what happens to R typically, and what is it on average? So the question is, if all elliptic curves over Q are ordered by their heights, what is the average size of the rank, that invariant R that we defined? Well, what's now become the standard conjecture, which is due to Goldfeld and Katz and Sarnak, is that this average rank should be 1/2. And in fact, more precisely, one expects 50% of all elliptic curves to have rank 0, and thus finitely many rational solutions, and 50% to have rank 1, and thus infinitely many rational solutions. So the expectation is that finite and infinite happen exactly half and half. And this is not to say that, so 0%, in other words, this implies that 0% of curves should have rank at least 2. That's not to say that no curves have rank 2 or more. It's just saying that density-wise, the expectation is that they should occur 0% of the time, 0 density. So this is the standard conjecture due to Goldfeld and Katz-Sarnak. But previously, this average has not even been known to be finite, let alone a half. So it was perfectly conceivable that as a and b get larger and larger, the number of rational solutions gets larger and larger too, and the rank just grows forever. The conjecture is that it's a half, but it was not even known to be finite on average, at least not unconditionally, and I'll say that something about that in a second. I also want to mention that computations do not give much support to this conjecture either. It was observed in the 1990 computations of Brumer and McGinnis that as they computed more and more elliptic curves of larger and larger height and computed their ranks, they were finding that rank 2 curves were occurring with increasing frequency. They were recurring surprisingly often and with increasing frequency. The conjecture says that they should occur 0% of the time. And these computations were recently extended by Bektemirov, Stein, and Watkins. And so here's a picture I got from them. So here's a graph of all elliptic curves ordered by conductor, starting at 100,000 and going up to 100 million. And what this graph is showing is the average rank of all curves up to that conductor. And as you can see, so once you start with all the curves up to 100,000, the average rank is already bigger than a half. And then it's only getting bigger as you're going to higher and higher conductor. So this is not very good evidence for saying that the average rank is a half, given that the average rank is just increasing. And it's not even clear whether the average rank seems to be approaching an asymptote around 0.87 or something higher, or whether it's increasing forever. But it's certainly, the least possible thing certainly seems to be that the average rank is a half. So I asked my colleague Peter Sarnak when I first saw this graph. He's one of the people on this conjecture. I asked him how he could possibly believe his conjecture given this data. And he looked at it for a second and thought, it's clearly going to turn around and approach a half. So he has very high confidence in his conjecture. And all three of them do, in fact. The first theoretical evidence towards the boundedness of average rank, because the graph doesn't even make it clear that you should expect boundedness of the average rank, since the average rank seems to be going up. The first theoretical results toward the boundedness of average rank are due to Brumer. So in 1992, Brumer showed that if you assume the generalized Riemann hypothesis and the Birch-Swinnerton-Dyer conjecture, that they together imply that the average rank is bounded. So the standard joke here is that if you assume $2 million worth of conjectures, then it is true that the average rank is bounded. But this was a major breakthrough because people do believe the generalized Riemann hypothesis and the Birch-Swinnerton-Dyer conjecture. And so if you believe those two conjectures, then you should believe that the average rank is bounded. And in fact, Brumer shows that the average rank is bounded by 2.3. So he even got a fairly small bound on the average rank using these two conjectures. In 2004, Heath Brown, still assuming GRH and BSD, improved this to average rank less than or equal to 2.0. And in 2009, Young further improved this, again assuming GRH and BSD, to less than or equal to 1.79. And this was very significant. This was a very significant breakthrough to bring it from 2.0 to 1.79, because what that now means, if the average rank is 1.79, that means that a positive proportion, at least, of elliptic curves have rank 0 or 1, right? Because the average rank is strictly less than 2. So a positive proportion are going to have rank 0 or 1. Remember that the conjecture is that 100% have rank 0 or 1, but at least this was giving a positive proportion, having rank 0 or 1, under the assumption of GRH and BSD. Anyway, this was a very exciting question for me because the data seems to totally not support even boundedness of average rank, while GRH and BSD imply boundedness of average rank. And so this was a very tantalizing question to get to the bottom of whether the average rank is indeed bounded. It would probably be the most interesting if average rank wasn't bounded. That would disprove either GRH or BSD. Okay, so this question of boundedness of average rank was something that was very exciting for this reason, that standard conjectures implied it while data completely didn't support it. So the question is, can one say something without assuming conjectures? And that's what I want to talk about. I want to talk about an unconditional proof of the finiteness of average rank. So this is a theorem that's proven just a few years ago in joint work with Ariel Schenker. The theorem is that when elliptic curves y squared equals x cubed plus ax plus b are ordered by height, the average rank is in fact bounded. And in fact, what we can now show is that the average rank is less than 0.89. And this is not assuming any conjectures now. This is unconditional. The average rank is definitely less than 0.89. It's interesting that we get 0.89 because if you looked at that graph, the graph was going up to about 0.87. Make of that what you will. A corollary of this, since the average rank has now been shown to be less than 1, what that means is that a positive proportion of elliptic curves must have rank 0. Otherwise, you couldn't possibly have an average rank of 0.89. So when all elliptic curves E over Q are ordered by height, a positive proportion have rank 0. In fact, at least 11%. In other words, a positive proportion of elliptic curves over Q have finitely many rational solutions. That's what that means. So a positive proportion of elliptic curves have no, in fact, remember I said that T, that finite group T is generically trivial. So what this corollary is actually showing is that a positive proportion of elliptic curves have no rational points at all, no rational solutions except for that point at infinity. Okay, so we expect 50% to have rank 0, but at least we now know that a positive proportion have rank 0, and thus no rational points except the point at infinity. So this work was work over a few years. And more recently, we now have an unconditional proof of the positivity of average rank. So the upper bound is 0.89, but we now actually have a lower bound. So this is a theorem in recent work with joint with Chris Skinner, that when all elliptic curves E over Q are ordered by height, a positive proportion of them also have rank 1. In other words, a positive proportion of elliptic curves have infinitely many rational points. And a corollary, therefore, is that when elliptic curves are ordered by height, the average rank is strictly positive. In fact, we show a lower bound of about 0.2. So the average rank is now sandwiched between 0.2 and 0.89. And 0.5 is pretty much in the middle of those, more or less. But these two theorems together do now show, therefore, that, with positive probability, an elliptic curve will have no rational points except the point infinity, and a positive proportion will have infinitely many rational points. So they both do occur in significant proportions. Okay, so a positive proportion of elliptic curves have no rational points except the point infinity, and a positive proportion have infinitely many rational points. And I should mention that the same results hold for degree 4 hyperelliptic curves as well. The reason being roughly that, well, remember the degree 4 case also corresponds to genus 1 curves, and so a lot of the techniques can be carried over. So when you look at y squared equals f of x, where f of x ranges over degree 4 polynomials, a positive proportion have no rational points, and a positive proportion have infinitely many rational points. That is also now proven. What about analytic rank? So it turns out I defined an invariant called the rank. There's another invariant of elliptic curves called analytic rank, which I won't define precisely, but given an elliptic curve, the Birch-Swinnerton-Dyer conjecture predicts that a certain analytic rank, this analytic rank is another invariant of an elliptic curve defined analytically instead of algebraically. It's defined as the order of vanishing at s equals 1 of a certain complex analytic function called the L function of the elliptic curve. So using an elliptic curve, it turns out you can define a complex analytic function, and you can look at the order of vanishing of that complex analytic function at s equals 1. That's some integer greater than or equal to 0. That's called the analytic rank. And the Birch-Swinnerton-Dyer conjecture predicts that this analytic invariant called the analytic rank is equal to this easy invariant that we defined algebraically called the rank. Easy to define, hard to compute. This one turns out to give another way of computing that same invariant. If they were always the same, it turns out that would give you an algorithm to always determine the rank of any given elliptic curve. That's why this conjecture is so important. It would sort of solve the problem of understanding how many rational points given elliptic curves have. Okay, the rank is equal to analytic rank. That's the Birch-Swinnerton-Dyer conjecture. And it turns out that if we combine these results on average rank with the work of Skinner and Urbain on what's called the Iwasawa main conjecture for GL2, which I won't say what that is. So combining with that work of Skinner and Urbain, we're actually able to show similar statements for the analytic rank, not just the rank. So the similar statement being that when all elliptic curves over Q are ordered by height, a positive proportion of them have analytic rank 0. And since these curves are a subset of those curves that had rank 0 in our construction, a positive proportion have both rank 0 and analytic rank 0. That's something that comes out of this theorem. And similarly, applying these same techniques to the joint work with Skinner, we're able to show that when all elliptic curves E over Q are ordered by height, a positive proportion of them have analytic rank 1. And in each of these cases, these analytic rank 0 and analytic rank 1 curves that we construct are subsets of the rank 0 and rank 1 curves that were constructed. And so a corollary of either of these theorems is that a positive proportion of elliptic curves do satisfy the Birch and Swinnerton-Dyer conjecture. And in fact, there are positive proportions that satisfy the Birch and Swinnerton-Dyer conjecture with rank 0 and a positive proportion that satisfy with rank 1. We worked hard this last few months to try and quantify what this positive proportion is. Is it really tiny? Is it like 1% or less? Or is it significant? So optimizing these proportions these last few months, just last month we posted a paper where, so this is joint work with Chris Skinner and Wei Zhang, where we work out this proportion And we show that this proportion is in fact greater than 66.48%. In other words, more than 66% of elliptic curves satisfy the Birch and Swinnerton-Dyer conjecture. So if you pick an elliptic curve at random, it's more likely than not that it satisfies the Birch and Swinnerton-Dyer conjecture. Okay, so that's what I'll say about elliptic curves. I want to ask next, what about general hyperelliptic curves if you go to higher degree? So we can order all hyperelliptic curves of any genus in the same way. Namely, we let A0 through AN run over the integers, allow them to get bigger and bigger. We'll define the height in terms of the absolute values of the coefficients A0 through AN, and we'll run over all hyperelliptic curves defined in this way. And remember that we know by Falting's theorem that hyperelliptic curves of genus bigger than 1, so in other words, n bigger than 4, they have only finitely many rational points. Okay, so y squared equals f of x, where f of x is a polynomial of degree at least 5, always have at most finitely many rational solutions. But what I want to, remember I said that there's no known algorithm, even though we know there are finitely many solutions, there's no known algorithm to find those rational solutions. But what I want to ask is, how many points do we expect typically such a curve to have? We know that there are finitely many solutions for such curves, but what happens typically? If we pick a random hyperelliptic curve, how many rational points do we expect to have? And so the theorem here, which is joint work with Dick Gross, together with work of Poonen and Stoll, and together with a recent preprint that's on the archive, the theorem is that suppose you fix the degree, any degree, at least 6, then most, in other words, more than 50% of hyperelliptic curves of degree n have no rational points. And moreover, the density of hyperelliptic curves having no rational points approaches 100% as n goes to infinity. So what this is saying is that if you pick a random polynomial over the integers, the chance that it takes a square value is essentially 0 once the degree is large enough. In fact, if you take a polynomial of degree 10 at random, so this rate of approaching 100% is exponentially fast. So if you're already at, say, degree 10, if you pick a random degree 10 polynomial, it turns out that with better than 99% probability, that polynomial will not take a square value. That's a consequence of the proof of this theorem. So once your degree is reasonably large, like at least 10, the chance that your polynomial takes a square value is negligible. So what this is saying is that Falting's theorem tells us that there are finitely many points on any given hyperelliptic curve, but in truth, most hyperelliptic curves actually have no rational points, no rational solutions. Okay, so that's what happens in the case of hyperelliptic curves. I should mention that it's natural to, most likely what's actually happening, standard conjecture in the subject that many people have made independently and which naturally comes from this work as well, is that once the degree is at least 5, if you pick a random polynomial of degree at least 5, the probability really should be 0 that it takes a square value. This is showing that result as n goes to infinity. Okay, so that's the case of general hyperelliptic curves. I want to spend a couple of minutes on the method of proof. So although the proofs behind these theorems all vary, depending on genus, they do have one important common feature. Namely, in each case, what we do is we identify a suitable representation V of an algebraic group G defined over Z. Okay, so an action of a group over Z on a vector space, lattice points in a vector space over Z. So it's some algebraic group, like SL2Z, for example, acting on some lattice. We identify such a group action, and then we find an explicit mapping from rational points on our curves to orbits of this group action. So in other words, a mapping from rational points to lattice points in a real vector space up to the action of some group. So it's a way of translating rational points into group theory. Find a map from rational points into orbits of a group action on lattice points in a real vector space. And once we have this map from rational points into lattice points in a vector space, then what we do is we show that such lattice points in the vector space that can be in the image of this mapping are relatively rare. And that's done using geometry of numbers techniques to count lattice points having bounded invariants, bounded coefficients of the equation on which we are finding those rational points. Okay, so if we take the image of this mapping from rational points to these lattice points, but we restrict the coefficients of the polynomial, then that gives certain bounds on the possible coordinates of the lattice points. And then by geometry of numbers, we try to count those lattice points, show that they're rare, and therefore there couldn't have been too many rational points. That's the technique. And I want to give you an example just to see how this works. So I'll give you the example of genus 2 hyperelliptic curves. Turns out every genus 2 curve is hyperelliptic, so you can just say genus 2 curves. The representation that we use for genus 2 curves, y squared equals a degree 6 polynomial, is the action of SL6 on pairs of symmetric 6 by 6 matrices. Okay, so we're going to talk about pairs of symmetric 6 by 6 matrices with integer entries. And SL6 naturally acts on pairs of symmetric 6 by 6 matrices by change of basis of the bilinear form. So you multiply on the left and on the right by the transpose, right, on both of them. Okay, so how are we going to map? We're going to map rational points to pairs of symmetric 6 by 6 matrices. Rational points on y squared equals degree 6 polynomial. We're going to map such rational points to pairs of symmetric 6 by 6 matrices as follows. So first of all, by a suitable change of variable, if we have a rational point, there's no loss of generality in assuming that this rational point is located at x equals 0, just by translating x. And so x equals 0 being a square means that a6 is a square, right? And so what we're assuming is that a6 is c squared for some c in z. Okay, so we can assume, if we have a rational point, we might as well assume that it's at x equals 0, and therefore a6 is a square, say c squared. We're going to associate to this rational point 0, c on our hyperelliptic curve the pair of symmetric matrices, the following pair of symmetric matrices. Okay, so we have this rational point 0, c. We're going to associate to it the following pair of symmetric matrices. Okay, very explicit map. So to this rational point, we associate this pair of symmetric matrices. And what's special about this pair of symmetric matrices? Let's call these two matrices A and B. Then what's special about this pair of symmetric matrices is that if we take determinant of ax minus b, where x is a variable, turns out we recover our original degree 6 polynomial. So given a rational point on y squared equals f of x, we've constructed a pair of integral matrices a and b such that the determinant of ax minus b is the original f of x. And notice that to construct this pair of matrices, we really needed to take a square root of a6. Right? This pair of matrices is going to be defined over the integers only if that c is an integer. And that c is the square root of a6. So we're really using the fact that this polynomial was taking a square value. On the other hand, what we show by now geometry of numbers arguments, that most polynomials f of x don't have a corresponding pair of matrices a and b such that determinant of ax minus b is f of x. So most polynomials don't have any such a and b such that determinant of ax minus b is your given polynomial. On the other hand, when the polynomial does take a square value, here's an explicit pair of matrices that does give your polynomial. Those two facts together say that most polynomials cannot take a square value. Most hyperelliptic curves cannot have rational points. Because if you take a square value, if your polynomial takes a square value, you get such a pair of symmetric matrices. On the other hand, we show by geometry of numbers arguments that most polynomials f of x don't have such an a and b, such that determinant of ax minus b is f of x. And that's the argument, and that's very typical of the arguments for many of the theorems that I talked about today. It's about finding correct maps into places where you can count things and show that they're rare. Okay, so to summarize, remember that a hyperelliptic curve over Q is an equation given by something like y squared equals f of x, where f of x is a polynomial of degree n and the coefficients are integers. That's a hyperelliptic curve. So in other words, we're looking for solutions to a polynomial taking a square value. That's a hyperelliptic curve. And the case n equals 3 gives elliptic curves. And so joint work with Arul Shankar and Chris Skinner now proves that the average rank of elliptic curves, in other words, the rank of the group of rational solutions to elliptic curve equations, in case n equals 3, that average rank is strictly greater than 0 and strictly less than 1. And therefore, a positive proportion of elliptic curves have rank 0 and thus no rational points. And a positive proportion of elliptic curves have rank 1 and thus infinitely many rational points. And these same results hold also for n equals 4, which is also a case of genus 1. And then joint work with Dick Gross and Poonen and Stoll and this recent preprint together say that for n bigger than 5, most, that is more than 50% of hyperelliptic curves of degree n, have no rational points. And moreover, as n goes to infinity, a density approaching 100% of hyperelliptic curves over Q of degree n have no rational points. And this goes to 100% exponentially fast. So once your degree is even more than 10, it's a very, very negligible probability that a polynomial will take a square value. I should mention that, notice the assumption here was that n is bigger than 5. The case n equals 5 remains open. We don't know that a positive proportion in the case n equals 5 of hyperelliptic curves have no rational points, although that's probably true. And there's some methods that that should handle it. But at the moment, n equals 5 is that middle case that remains open. Okay, I think I'll stop there. Thanks very much for your attention.
Are there any questions?
Yeah.
You say that a positive proportion has rank 1. How do you know the average isn't coming from curves of a higher rank?
So if you have a positive proportion of curves that have rank 1, then that's enough to say that the average rank is positive, right? Because a positive proportion of the ranks, when you list them, will be bigger than 0. And so that's what gives that, that the average rank is strictly positive. None of these results...
How do you know that you don't have 44% with rank 2 and none with rank 1?
That we don't, yeah, so we can't rule out the fact that a positive proportion of curves might have rank at least 2. That doesn't follow from any of the theorems that I said. So it's possible that there are lots of curves of rank 2. But there can't be too many of them because the average rank is at most 0.89. That's also a theorem.
Other questions? Yes, please.
I have one.
Okay, so the question is, does this work say anything about the behavior of T, the torsion group? And the answer is that actually that's a fairly elementary, there's a fairly elementary argument to say that this torsion group T is 100% of the time trivial. So it rarely occurs that T is bigger than trivial.
All right, as we're slightly over time, one more question.
I had a question. So, okay. I guess you're not entitled to 66.48% of $1 million. No, that's not my question, actually. My question is, so this Stein and Watkins graph, what's going on there? Is this just noise for small coefficients of elliptic curves? And do you or Synack have any idea of when it's going to get close to 1/2? How far is there any hope to extend the computations to get to a point where it sort of looks remotely like 1/2?
Right, so that's a great question. So the question is, what's going on with that graph, and why does it seem to contradict everything that the results are currently saying? I should say that a lot of these methods that have been introduced to handle average rank of elliptic curves, if taken to their completion, they naturally lead to the conjecture and maybe eventually to the proof that the average rank should be a half. That is naturally coming out of the proof at this point. So I actually believe, even though I was skeptical when I started on this question, I actually believe that the average rank is a half now. And so the question is, why doesn't the data support it? I think it just means that 10 to the 8 is still a fairly small number. And we should, if we take the so yeah, it's probably small number noise. There's an error term in these asymptotics that are probably bigger than the main term when your numbers are small. And actually there's a big group now trying to take these computations significantly further, a couple of orders of magnitude further. So, and they're hoping that just with a couple of orders of magnitude, say up to 10 to the 10, you might start to see it turn around. Or even if it doesn't turn around, if it continues to go up, if it passes 0.89, that would also prove that eventually the graph has to turn around. Because the average rank is proven unconditionally to be less than 0.89. So if we take the computation far enough so that it crosses 0.89, that even though we don't see it turning around, that proves that it will turn around.
All right. Well, let's thank Professor Bhargava for this wonderful
Thank you.